In this question, what we want to do is prove 2 to the power of n minus 1 is divisible by 3. So it's going to be a little bit difficult because it's got 2 to the power of n. So again, it's true for all even positive integers. So we start with n is equal to, that's our lowest even positive integer. So 2 to the power of 2 minus 1 gives us 4 minus 1, which is 3, divisible by 3. So it's true, it works for n is equal to 2. We're going to assume it's true for n is equal to any positive integer, even integer. So n would be equal to 2 to the power of k, so because that's going to give us an even number. So 2 to the power of 2k minus 1 divided by 3 equals m. And then I've manipulated to get 2 to the power of 2k is equal to 3m plus 1. So I'm doing that manipulation as normal. So this time let's prove that it's divisible by 3 for 2k plus 2, which would be the next even number. So we do substitution of 2 to the power of k plus 2, which is 2 to the power of 2 times 2 to the power of k. So which is 4. Then we can do our substitution of 2 to the power of 2k is 3m plus 1. 4 outside of that can be expanded. Minus 1. 4 minus 1 gives us 3. Factorise the 3. We're divisible by 3. So it's true for any even number. Question 4 is a little bit harder. Now, again, we're going to have to look at the manipulation and we've got to understand the series here. So the series here goes up and we add the first n integers and then we start to subtract. Start to subtract 1 away and we go back down to 1. So if we have a look there, and it's really important to realize that every term is repeated in that process except for the middle one. The middle one's the only one where we've got only one of each of that term. There's 2 1s, 2 2s, 2 3s, right through to 2 lots of n minus 1, but only 1 lot of n. And that sum is equal to n squared. So show it's true for n is equal to 1. Well, if n is equal to 1, there's only the one term, so 1 is equal to 1 squared. That's true. So if we're assuming it's true for n is equal to k, then we sum the consecutive integers up to a point k, and then we sum the decreasing consecutive integers back to 1, and that would be equal to k squared. So remember, as we said, everyone's got 2 terms except for k, which is important in the next point, because what we want to prove, required to prove it's going to be equal to k plus 1 all squared. So if we have a look at what we've got, remember we added integers up to the point k, but now we go to the point k plus 1, and then we go down from k, k minus 1, and so on. Now if we compare that to the previous part, so it's equal to k squared. That part's equal to k squared. So we went up to k, but then down from k minus 1. Really, everything in here is part of the sum of the first k terms, except for those two. They're the only really 2 terms we add in the sum of the first k plus 1 terms, because we went up to k and then we went down from k minus 1 back to 1. So really, these terms here that underlined there are going to be equal to k squared. And then we've added the k plus 1 plus k. So there's the trick in this one. So we've got to be able, again, if you don't understand the series, you're probably not going to get this question. So it's really important you understand the series that you start off with. So, and then we can say, well, k squared plus 2k plus 1 will give us k plus 1 all squared. So that's once we've got to that point, it's pretty easy. It's understanding the series that is the hard part here. And understanding, well, what happens, where do the terms come from, how do we write our left-hand side, which would be tricky. So again, understand, there's lots of things going on. Understand the algebra, but also understand really well what the series is that we've got to find.